Hey, good evening, everyone. I'm Gopa Parameswaran from Microsoft. I work for the Cloud AI and Advanced Systems Engineering Group. Today, I'm going to talk about a modular chassis, Shasta, we developed in collaboration with Molex and Quanta. So majority of devices we deploy today in our data center are general purpose CPUs. So we design one RU boxes or two RU boxes with these devices, put it into our one of the standard racks like Olympus, then deploy it in our data center. So with this rack, we get powering strategy, cooling strategy, then form factor, and connectivity. In our data center, we have a out-of-band network for management, and then there is an in-band data plane for the workload and some of the management functions. In addition to that, we also have a set of deployment tools which we use in deploying the devices into our data center, and they belongs to, or they support onboarding activities, health monitoring, then run diagnostics in case if we have any issue with the hardware, and help with the repair activities. So all these tools reach the devices and the circuits around it through these two network which I mentioned. One is the management network, and the other one is data plane network. So that's the kind of established process we follow for deploying the servers in our data center. So moving forward, what we are seeing is a large set of domain-specific devices coming into our data center. And the process to deploy these devices are not very well established right now. It's getting established. The one option we have is to take these devices and the systems designed by the device vendors, then make necessary modifications to make it compatible with our data center, and then deploy them in the data center. So that customization is time-consuming, and it involves a lot of effort. The other option is to get the device in a PCI card or some such things and plug it into one of our standard server, then deploy the server in our data center. So that's actually faster way of deploying, but then we have to deal with the limitations of PCI card, like power limitation, cooling limitation, and also PCI don't support hot swap, meaning if any one of the blade fails, we have to take down the whole server, repair it, and that's a limitation, right? So that's the scenario in which we started looking for an alternate approach where if we have a modular chassis where the devices are plugged in and also can handle more higher power and thermal and cooling, that solution could enable more collaboration. So that's the direction. That's what led us to look for an architecture like Shasta. So here I have a simple block diagram where a chassis control module provide connectivity to the device modules and also extend sideband signals and management interface to the power board and also fan subsystem. And the picture I have here is an exploded view of Mount Shasta. And some of the features we were focusing while designing, one, of course, is the modularity, meaning which supports hot swap. Then the other one is how we distribute the power, then signal connectivity, and the air cooling. And this design was done with air cooling in mind. Our study shows we can cool something like 4,000 watts in this 4OU chassis. And at the device level, we can cool up to around 700 watts in certain configuration, meaning the die size, hot spots on the die, thermal attachment, and things like that. So the management responsibility of this chassis is with the chassis management module. And we have two subsystems in this. One is the PCI switch. The upstream port of the PCI switch is connected to an external head node. Then the downstream ports of the PCI switch is extended to the modules. So all these modules we have in this chassis will show up as a PCI devices to the head node. So from the data center infrastructure standpoint, it'll look like any other PCI card present in the servers, and it can be managed in that fashion. The DCSCA module we have in this chassis management module extends its sideband signals and also low-speed interfaces to all the device modules, fan subsystem, and the power subsystem. So we can monitor various sensors, just like the way server BMC monitor the sensors and manage the devices. So this architecture allows us to emulate a server-like interface to our data center automation tools and the hardware infrastructure. From the power standpoint, we pick up the 48 volt in the OpenRack V3 power bus bar and feed that 48 volt into a power distribution board. And in this design, we convert that 48 volt into an intermediate bus voltage, 12 volt. Then that 12 volt is then distributed to the modules. And this power distribution board can be easily modified to pick up any other intermediate bus voltage. Or we could even take the 48 volt and feed directly to the modules. We can also add a protection for each of the feeds going to the modules. Or we could even add the power monitoring and voltage monitoring and such. So essentially that power, if a design needs a different types of intermediate bus voltage, we only need to modify that power distribution board, and we can accommodate such requirements. And from the signaling standpoint, from the signaling standpoint, we have in this chassis, we have the PCI down ports extended from chassis management module to the device modules. And for this design, which I'm showing here, we have a Gen 3 by 4 downstream ports extended to the device modules. And this cable backplane can be easily modified to go higher in speed and larger in lane count. The way we attach this cable backplane to that holding structure shown there allow us to have a float for these connectors so we can absorb stress from the shock and vibration, which the heavy heat sink in the module might have. And those shock and vibration stress won't go into these connectors. Also, this holding structure can be moved forward towards the front of the chassis or back to accommodate different module form factors. That's another example of how this chassis can be customized for different design needs. So it's a simple solution that can help in collaborating with device vendors and ODMs to deploy non-GP CPU devices into our data center. We are in the process of releasing this specification to OCP, and we are going to release the design also to OCP pretty soon. So we think this is an opportunity to collaborate with industry and create a win-win situation for all of us. So that's pretty much my presentation is. Thank you.